so this video, we're just going to continue chapter 24, section 2, and we're going to look at the convex spherical mirror. Now, convex spherical mirror looks like this. Again, you can think of this as being the light side. This is where all your incoming and outgoing light is. And this side over here is dark. Okay? That's not very pretty. I'm going to draw a straighter line. Okay. Now what's different is if I draw the optic axis here, when you have a convex mirror, your center of curvature and your focal point are over here on the dark side. So let's suppose this has a center of curvature of about, that's 26 centimeters, so that'd be 13 centimeters, doesn't matter. This is the center of curvature, this is the focal length, this distance from here to here is R, it's the radius, whoops, that should be a capital F for focal point, and this distance is a lowercase f, that's the focal length. So center of curvature, radius of curvature, focal point, focal length, they're all defined just like they were for the concave. There's really one important difference. If you have, in this case, these quantities are not on the side of the outgoing light. So we consider it to have a negative radius of curvature, and we consider it to have a negative focal length. And that's really, really important to realize that if we have a convex mirror, that is a negative focal length, and that means that R is also a negative value, okay? The focal length and the radius of curvature are not on the side of outgoing light. In order to be positive, they have to be on the side of the outgoing light, okay? Where you see mirrors like this, the typical uses are security mirrors. If you ever go in the 7-Eleven and they have those mirrors up in the corner, those are going to be convex mirrors. And what they do, what you're going to see, is they form virtual images behind here, just like a plane mirror would do, but they're really, really tiny, and they allow you to get kind of a wide angle view. Another place where you see them is on the side mirrors of your car, and it'll have that little saying that says, objects in the mirror may be closer than they appear. And the reason that you might think they're farther away is because they'll be smaller. The magnification for this type of mirror is always less than 1. So you end up getting little tiny images. So if you look and you see a little teeny tiny car in your side view mirror, you might think it's really far away, and it may not be as far away as you think. But the convex mirror lets you get that wide angle view. So they're used, like I say, I think of them as the security mirrors in the 7-Elevens. Okay. As far as rays go, let's draw what the rays would do. I'm going to kind of erase some of the extra writing here and just keep the focal point. It's the interesting point. If we have a parallel ray coming in and it hits the mirror, parallel ray coming in, here it comes in. When it hits the mirror, of course, it has to reflect off the surface of the mirror. But it reflects as if it came from the focal point. So it came in parallel, and when it hits this mirror, it's going to go reflecting off as like it came from the focal point. Same thing, if we draw one down here, it's coming in, hits the mirror, it bounces off, and it reflects this way. Okay. When things reflect, your eye tends to track them back and see this image that forms back here. Okay. So if we think of the sun with a bunch of parallel rays, it would form an image of the sun back here. Let's go ahead and do an example. And I could have turned those around as well. If you have a ray of light that's directly pointed towards the focal point, when it hits the mirror, it will bounce off parallel and go this way. Remember, the path of the light ray is completely reversible. So any ray pointed directly towards this focal point will hit the mirror and bounce off parallel. Okay, let's do a problem. And in this example, it says that Santa sees his reflection this time of year. It might make more sense to have the Easter Bunny, but I don't know that the Easter Bunny has ornaments. So Santa sees his reflection in a spherical ornament that has a diameter that's equal to 7.20 centimeters. It's actually not an unusual size ornament, pretty typical. If Santa is standing .0 centimeters from the ornament, and is 1.60 meters tall. Where is his image? And how tall is it? Okay, so we've got this problem. We've got a little old Santa Claus here, and he sees himself in this ornament. What does he see? Okay, if the diameter is 7.2 centimeters, that tells me that the radius is 3.6 centimeters, and that tells me that the focal length would only be 1.8 centimeters. But this is a convex mirror, okay? So our focal length is going to actually be negative 1.8, okay? We know where his image is where the object is located. That's his object. So we've got F equals negative 1.8 centimeters, and we've got S equals positive 75 centimeters. So 1 over negative 1.8 has to equal 1 over 75 plus 1 over S prime. That's our 1 over F equals 1 over S plus 1 over S prime. We're going to put that in a calculator, and we're going to find out that S prime comes out to be negative 1.76 centimeters. So when he sees himself in that ornament, he sees a little teeny tiny Santa Claus that's just a little less than 2 centimeters behind the surface of the ornament, okay? To get how high his image is, we can say that y prime over y equals negative s prime over S. Notice that S prime is negative, so this will come out to be a positive. So Y prime, okay, he's 1.6 meters, but let's change that to centimeters. He's 160 centimeters. Negative S prime is 1.76 centimeters. S was 75 centimeters. And Y prime comes out to be 3.75 centimeters. So he sees a little teeny tiny Santa Claus. Notice it's going to be a virtual image. He sees it back behind the mirror. We can tell it's a virtual image because the magnification is negative. Sorry, I said that exactly wrong. The image distance is negative. When the image distance is negative, you have a virtual image. He's going to be upright. Virtual images are upright. That's what you get when you look in your bathroom mirror. Okay? If you wanted to know the magnification, it would be a very small number. It would be 3.75 centimeters over 160 centimeters. So the magnification is only 0.0234. Okay? So we get a virtual image. It is upright. It's 3.75 centimeters tall. And that concludes convex mirrors. The important thing to remember is that a concave mirror has a positive focal length. It can form both real and virtual images. A convex mirror like this one can only form virtual images, and it has a negative focal length. Just remembering which one's positive focal length and which one's negative focal length will help you a lot on the problems. It's a really important thing to pay attention to, okay? Concave, positive focal length. Convex, negative focal length. See you next time.